Okay, welcome back. Okay, so today we're going to continue. We're going to finish off Chapter 6, or the normal distribution. And today's topic, which is going to be a short one, and I'm not going to spend a lot of time on it because it has application from a theoretical point of view, but it's obsolete now with the graphing calculator. And that's using the normal curve to approximate the probability of a binomial distribution or a binomial variable. So historically, what we would do is if you wanted the probability for a binomial random variable, there was, let's say you had a sample size of 20 or less, then there was a table in the back of the book that you could just look it up. And, but if you had more than that, large values of n, because remember with the binomial, you're counting the number of x's, the number of successes, right? So x can be 0 all the way through n, right? So you have n trials. Well, for a number of trials that were 20 or less, then we had a table, or we could easily calculate those. But if it was bigger than 20, let's say, then we had to use the binomial formula, and those calculations got tedious and time-consuming. So using a normal approximation would simplify things. Now, why would we use normal? Well, it turns out that as you have a larger and larger sample, or a larger and larger value of n, that the distribution for a binomial variable becomes more and more bell-shaped and symmetric, which lends itself very very useful in using a normal approximation. Okay, so if we have a large value of n, and we can use the normal approximation, that would simplify our calculations. Instead of having to use the binomial formula, we can just use our calculator or use tables to calculate the probability using a normal distribution. Okay. So again, now that we have the calculator, we have binomial CDF and binomial PDF functions, so it makes this approximation obsolete. But again, it still is important when we get to later chapters, like Chapter 8 and Chapter 9, and we start talking about sampling distributions, or we start talking about confidence intervals and things like that. Okay, so again, so the idea here is if we have an x, right, and we know that x is binomial, with a n and p, and n is sufficiently large, then if n is sufficiently large, we can assume that it takes on a bell-shaped symmetric distribution, and we can use a normal approximation. And we'll talk more about when we get to sampling distribution, things like that, about how do we know it's normal. Okay, but historically, that's what we've been seeing. So what we can do is, again, you can, if you go to the book, the textbook, or if you do a Google search on binomial distributions, as far as when n increases, you can find all kinds of things that show that as n increases, the distribution, the shape of the histogram for a binomial distribution becomes more and more bell-shaped and symmetric. Okay, and so that fits really nicely with a normal distribution. So we can use a normal distribution as an approximation. Okay, so now, how big does n need to be? Well, typically, we're just going to, if n is bigger than 20. Okay, so that's what we're going to do. So if n is bigger than 20, then we're going to use a normal approximation here. So what's the normal approximation? Well, what do we use for the mean and standard deviation when it comes to a binomial distribution? Well, we use mu is equal to n times p, and sigma is equal to the square root of n times p times q. Okay, that's what we're going to use. Okay, so now what we're going to do is we're going to say, hey, we're going to use this information and say, okay, we're going to assume that that x is approximately normal with a mean of np and a standard deviation equal to the square root of NPQ. But when? There's a couple of conditions we have to meet. Okay, the two conditions is, well, obviously this, we have to have a large enough sample size, right? So we're going to use this, okay, n is greater than 20, but also we have to have the number of successes, right? The expected number of successes has to be what? Bigger than 10 in this case, and the expected number of failures also has to be bigger than or equal to 10. Now, if I remember, if we go back to chapter 5, chapter 4. So if we go back to chapter 4, and we talk about binomial, let's just review what the conditions were for a binomial. So remember, for a binomial case, we had those 5 conditions, right? And so in the binomial case, we had if there are only 2 outcomes, right? So only 2 possible outcomes, a fixed number of trials. The probability of a success is constant for each trial, so it doesn't change. And they're independent, right? So we have independent trials. And the random variable is defined a certain way as a counting variable. Number of x out of n trials, right? The number of successes. So in this case here, we're just going to introduce it as, hey, if n is sufficiently large, so bigger than 20, and also these 2 conditions have to be met, that the expected number of successes and the expected number of failures are both bigger than 10. If that's the case, then we can use the normal approximation, okay? Just be aware of that, okay? And that'll come up again later. Now, what do we use? Well, again, here's how we're going to do it. I'm going to do an example of what we would do in a moment. But this is what we would use for the normal approximation. Now, we also have to consider what we call a continuity correction. Okay. So in a continuity, correction, it's to make our estimates using the normal approximation even better. Okay, so we always add or subtract this continuity correction depending on the situation. And what we're going to do is we're going to either add or subtract 0.5. The 0.5 comes in from the fact that we're dealing with a binomial variable. Remember, it's a discrete random variable. So what do we have when we graph a discrete random variable? We get a histogram. Well, histograms have bars, right? And so the center of each bar is centered at the different values of x. So remember, x is 0, 1, 2, 3, and so on. So the middle of the bar is the x value. Well, how do we get from one class to the other? Well, we add and subtract 0.5, right, to get to the boundary. Well, one of the boundaries is going to be 0.5 plus above, 0.5 above the x value, and the other boundary, right, is going to be 0.5 less. So that's how we get our bars, right? Remember the width of a bar is 1 in the discrete case, right? So if we're centered right in the middle, and that's where x is, well, 0.5 above and 0.5 below is going to be where the boundaries of our histogram is going to be at. So what we want to do is we're going to include 0.5 or subtract 0.5 depending on what the probability is that we're asking for. Okay? And again, just realize this is the continuity correction that we're going to use. Now, the next example I'm going to do should make it clear what we're doing, okay? And I'm going to walk through it too. And then that'll be it, okay? So I'll do one example of how the normal approximation works, okay? So now, here's the example. So here we have a local kindergarten school district, so grades K through 12. So it's, well, local school district. It's K through 12, so kindergarten through high school. So now, what they found is that 53% of the population favor having a charter school for grades K through 5, so for kindergarten through 5th grade, okay? So that's going to be P. So P is 0.53, the probability that a randomly selected person is going to be in favor of a charter school in this school district. Now, they surveyed 300 people for this. Okay, so that's N, right? So N is large. So definitely bigger than 20, right? Definitely bigger than 20, right? Also, let's check our stuff, right? N times P, which is going to be, what, 300 times 0.53, and that's going to be 159. Okay, and so that's definitely bigger than 10. And then N times Q, now remember what Q is. Q is 1 minus P. So this is going to be 300 minus 0.47, but also this is also equal to what? Well, this is 159. Well, this is also equal to N minus what? X. Remember, this is the same as the expected number of successes. So out of the 300, how many people were in favor? 159. Well, how many people are not going to be in favor? Well, it's the same as N minus X. So 300 minus 159, and of course this is going to equal what? It's going to be equal to 151. No. Boop, 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 boop. It's going to be 141. Okay? Well, this is obviously also bigger than 10. So we've got all the conditions met. So this is a candidate for a normal approximation. So again, this is a binomial variable, right? So this does meet the conditions for a binomial in a binomial experiment. So X we know is binomial with an N equal to 300 and P equal to 0.53. Okay. So now what we're going to do is we're going to use the normal approximation, and we're going to say that, hey, X is approximately normal with a mean of what? P times N, right? So that's going to be 159. And a standard deviation equal to the square root of N times P times Q, which this turns out to be approximately 8.64. Okay, so what we're going to do is the next questions that we're going to answer is going to be using this information. Okay, so we're not using anything from binomial. We're going to use normal as an approximation. Okay, and this is what we're going to use for the parameters. We're going to use a mu of 159 and a standard deviation of 8.64. So let's do that. Okay, so let's take this information and we're going to write this. Okay, so now let's rewrite this. And now what we're going to do is we're going to use X is approximately normal with a mean of 159 and standard deviation of 8.64, approximately. Okay, so now, the first question that they ask, we want the probability, or they want the probability, what's the probability that a randomly selected, that the number of people who favor, okay, so again, So the probability is, they want to know what's the probability that the number of people who favor a charter school in the school district is greater than or equal to 150. So that X is greater than or equal to 150. And what we're going to do is we're going to use a normal approximation. We're going to use normal CDF. Oh, hold on a second. Before we do that, let's talk about the continuity correction. I was thinking about it, but I think it's more appropriate. It'll be better to talk about it here. So now, this is our X value, right? So let's think about this. We're including this value in our probability, right? So we want to include the entire bar. So think about, this is a histogram. This is a binomial distribution. So think about the bar. So let's just think about one piece of the bar, right? So here is my bar, right? So right here is 150, okay? Now, let's say this is the other bar. Okay, let's say the bar over here, and let's say we have another bar over here, let's say. Oops. Okay. Now, 150 is included in our upper bound, right? So we want to include this entire bar as part of our probability, right? Area, right? Well, if we do greater than or equal to 150, well, what we're doing is we're missing this piece right here. We're only including everything to the left if we do that, right? If we use that. So what do we need to do? Well, we want to include this end of the rectangle. So that means, well, how far do we have to go over here, right? So how far do we have to go over? 0.5, right? Because if this is 149, well, what's the distance between them? Remember, class boundaries. It's going to be 0.5, right? So that's where the continuity correction of a half comes in. Is we're going to subtract 0.5 because why? We want to include this part of the bar. We want to include all of this. So now what we're going to do is we're going to subtract 0.5 from this. So now it's going to be greater than or equal to not 150. We want the probability that X is greater than or equal to 149.5. So that's the continuity correction that we want to add. Now, this is what we're going to use now to get a more accurate approximation. So now what we're going to do is we're going to use normal CDF. And now our lower bound is what? It's going to be 149.5. And our upper bound, again, is going to be 10 to the 99th power. Our mean is 159. And our standard deviation is approximately 8.64. And so when we stick that in our calculator, we are going to get 0.8642. And that's our answer. Okay? I hope that makes sense. Okay? So now, let's do the next one. So now, B says, I want the probability of being less than or equal to 160. So what's the probability that less than or at most, what's the probability that at most 160 people will be in favor of a charter school? So that's going to be less than or equal to 160. So now B says, hey, I want the probability that X is less than or equal to 160. Okay, so now let's talk about the continuity correction again. Okay, so let's draw our bar again, right? So here's our histogram. So, because it is a binomial distribution, right? So let's say we have our bar over here, and let's say we have our bar over here, right? Now again, 160 is going to be right in the middle, right? So that means if we go out a half this way, right? If we go out half this way, this is going to be 160.5. And if we go out a half this way, this is going to be 159.5. Now, here's the thing. This says less than or equal to, right? This is less than or equal to. We want 160 included in this. So it's going to be 160 or less. So if we do 160 or less, we want this entire piece to be included, right? Because it's part of the bar. So if we just do 160 and use the normal approximation, we're going to include all of this and all of this and everything to the left. And what are we missing? We're going to miss this piece here. So we want to add 0.5 to make sure that we get all of this. And so that's what we're going to do. So if we add 0.5, then what we're going to say is this probability is approximately equal to the probability that x is less than or equal to 160.5. And so now that's what we're going to use. So we're going to use Normalcdf. And the lower bound in this case is going to be negative 10 to the 99th power. Now you could also use what? 0, right? Because you can't have less than 0 people in favor, right? So you could use 0 here, and that would be fine. So 0, and now the upper bound here is going to be 160.5. The mean is 159, just like before, and the standard deviation is 8.64, approximately. And so now, what do we get? Well, let's put it in our calculator. And so we're going to put in 0, 160.5, 159, 8.64, and enter. And we get 0.689. 0.689. 0.68. Oops, hold on, I'm missing one. 5689. 0.5689. And so that's the probability. So, makes sense? So again, as far as whether you add or subtract the 0.5 for the continuity correction, depends on what you need to include or what you need to exclude. Okay? So in this case, we wanted to include the bar. Okay? So we added or subtracted 0.5 to include half the bar that would have been cut off. Okay? Now, let's go to the next one, C. Now C says, hey, I would like to know what the probability is that more than 155 people would be in favor of a charter school. So in this case here, I want the probability that more than 155. So that x is greater than 155. Well, now I want to exclude 155 from the calculation because it's greater than 155. So again, if you just draw the histogram a little bit, just like a zooming in of one, right? And it doesn't matter how you draw it. So here, let's say here's 155, right? 155, smack dab in the middle. And of course, we don't want to include this. It's greater than. So we want everything to the right. Right? So we want starting here. Right? So we don't want to include 155, which means that if we use the normal approximation and we use 155, we're going to be including this piece here, okay? Because remember, the normal approximation is a continuous random variable, right? If we say we want to include 165, if we say put 155 in there, if we put in 155, it's going to calculate right from 155. But remember, in the discrete case, if we say we exclude it, we want to exclude it. So we want to make sure that we don't include anything from here. So what are we going to do? We're going to add 0.5 to make sure we're right here at this boundary, this class boundary. So if we add 0.5, right, we're going to get 155.5. So what we're going to do is we're going to use the approximation, and we're going to say x greater than 155.5. Okay? I hope that makes sense. Okay? I hope me drawing the pictures makes sense, because when you read in the textbook, it's hard to visualize. Okay, so draw a picture. Okay, so in this case here, now what we're going to do is we're going to use normal CDF, and we know what to put in now. So the lower bound is what? This, 155.5. The upper bound is going to be what? It's going to be 10 to the 99th power. And of course, the mean and standard deviation are the same, 159 and 8.64. And so what do we get? We get 0.6572 for our probability. Okay? That's it. And the last one I'm going to do is similar. But now we're going to say less than. So now part D, says, hey, what is the probability that fewer than 157, so less than 147, favor the charter school? So now here, again, we want to exclude 147. We don't want 147. We want that bar for the histogram not included. Okay, so if we look at the bar, right, and this time I'm not going to include the other bars, but if we have the bar here, we have 147, right? And it's less than. So we want everything to the left of this boundary, right? So what's that boundary? Well, it's going to be 0.5 away, right? So this will be at 146.5 because this is 0.5 away, right? Okay? So now what we're going to use is 146.5. And so we're going to use approximately, the probability is going to be equal to x is less than 146.5. And we're going to use the normal approximation. And so again, this is going to be equal to normal CDF. And now the lower bound is what? 0, right? It's going to be 0 because, again, we can't have less than 0 people who favor. And then the upper bound is going to be 146.5. And 159 is the mean, and 8.64 is the standard deviation. And again, if we plug that into our calculator, we get 0.0741. That's it. So I hope all of these parts of this example helps you realize why we do the continuity correction in the first place. Okay? And it's all based because we're trying to take a discrete probability distribution binomial and approximate it with a continuous probability distribution normal. Okay? So that's why. Okay? Now let's do the last one, E. Now this is going to be, again, different. Okay? And you'll see why. So here is the question. E says this. What's the probability that x is equal to 175? Okay, now here's the thing. What is the normal approximation for equal to? It's a continuous distribution, which means if we use the normal approximation for this, the answer is always going to be what? 0. So we don't want to do that because that's not accurate. That's not true. Okay? Well, here's the thing. We could, in this case, just use the binomial formula, right? Because it's only one calculation. Okay? So in this case here, I would just use the binomial formula. So go right back to the fact that this is a binomial distribution. This is a binomial random variable, right? So all the other ones, we did the approximations because it was easier, it was simpler, okay? Because if we didn't have the calculator, in other words. Here, we could just use a table for normal, okay? Or use the calculator. So in this case here, I can use the binomial formula, which would be easier. So in here, you would be 300 C 175 times P, right, to the 175 times Q to the what? 1 minus that. Or actually not 1 minus that, n minus that. So n minus this, which is what? It gives us 125. And so I can easily stick this in my calculator and just find out what is the number of combinations. So, and this is 0.53, remember? So P is equal to 0.53 and Q is equal to 0.47. So I can just plug and chug at this point. So if I do 300 and then do my probability, my combinations, and so I do, what is it, 175, okay? And so I times that by 0.53 raised to the 175th power, and then times that by 0.47 raised to the 125th power. And so my probability turns out to be 0.0083. 0.0083, and I'm done, right? Well, did they do the same thing? Let's find out. So here's what we need to do. Instead of doing it that way, if we wanted to use the normal approximation, think about the bar again. Okay? So here's the bar. It's centered at 175, right? Well, what's the width of the bar? Remember, the width of a bar for a binomial random variable, it's always 1, right? So if we go out 0.5 this way, it's 175.5. If we go out 0.5 this way, this edge here is 174.5, right? And so for the normal approximation, we're going to use this and this as our upper and lower bounds. So this would be our lower bound, this would be our upper bound, and that's it. That's how we would do it. So let's do that. So here we're going to say this is approximately equal to the probability that x is less than what? 175.5 and greater than 174.5. And so to use the normal approximation, well, it's just going to be the lower bound is 174.5, the upper bound is 175.5, and then 159 and 8.64. Let's see what we get for that one. And we get the same thing, 0.0083. So look at that. We get the exact same answer with the normal approximation. That's how accurate it is. Okay? So other than that, that's how we would use the normal approximation for binomial in these types of cases. Now, again, with the calculator, we have Binomcdf, Binomcdf. So doing these as normal approximations are obsolete now. But again, when we get to later chapters, this is going to become important theoretic in theory. Okay? So again, that's all I have to say. Enjoy, and I'll see you next time. And this ends our Chapter 6 material over normal distribution. Thank you. Okay, welcome back. And today we are going to talk about a new topic, and it's going to be on the central limit theorem. Okay, so last time we talked about the normal distribution. And so all the consequences that we get from the normal distribution, all the things that we can do with the normal distribution. This topic is now deciding or talking about things like, what about distributions that involve things like the sample mean or the sample proportion, the sample, those types of things. And before we had talked about, we had talked about and discussed in Chapter 1 we talked about this idea, or in Chapter 2 we talked about this idea of the sample mean. So let's start with the sample mean and give an idea of what we mean by when we talk about sampling distribution, and then talk about the central limit theorem, which is what this chapter is mainly about. And the central limit theorem is probably the most powerful idea in all of statistics, and is used in many situations. You'll see why. But if we talked about if we took a sample, right, of size n, and we calculate the sample mean, right, and if we do that again, we take another random sample of the same size, and we calculate the sample mean for that one, chances are those two sample means are going to be different, right? And they're definitely probably going to be different than the true population mean mu, right? And so what happens if we were able to continue to do this? What if we were able to calculate all possible sample means from a random sample of the same size? Well, we would get a distribution, wouldn't we? I mean, if we're taking a random sample, right, it's a random sampling method, right? And we're just taking a random sample of size n. We calculate the random, we calculate x bar, right? Then we do it again. We take another random sample of size n and we calculate x bar. Wouldn't then x bar be a random variable since it's changing from sample to sample, and our samples are gathered by a random sampling method, right? Then it would stand that x bar is a random variable in that case, right? And if we were able to calculate all the possible values of x bar based on the same sample size, what would that distribution look like? Well, if we think about it, it would make sense that the average of the averages, so if we took all of the x bars and we calculated the average, that all of those averages, all of those x bars, all those sample means should hover around the true mean, right? So if we were to take all possible values of x bar and take the average of all of those possible values, the average of those averages, right, the average of the means should equal mu, or should be very close to mu with very little differences. Okay, so that's one thing. The other thing too is we would also expect that the PDF right, the probability distribution function would decrease, right? Right? The probability of getting further and further away from the middle there should get smaller and smaller, right? I mean, as you get further away from the mean, the probability of such a thing should get smaller, right? And also, you would expect that it would make sense that the likelihood of being overestimated, right, on a sample, or underestimating on a sample should be about the same, right? So it makes sense from an intuitive perspective that it would be bell-shaped and symmetric, right? And so what the central limit theorem does is it validates what we would expect, or what intuition tells us what we would have if this was the case, if we were able to do this, right? So what the central limit theorem basically tells us is, it says, hey, if we have a large enough sample size, then the sampling distribution should be approximately normal. Okay, and that's where we're going. Okay, so when we talk about a sampling distribution, we are talking about what is the distribution of our sample statistic. In other words, if we're talking about x bar, what is the distribution of x bar if we were able to calculate all of the different values of x bar we could get if we were to take the same sample size over and over again? Okay, so, or in other words, what's the sampling distribution of p hat? In other words, what kind of distribution does p hat have if we were able to calculate p hat for all possible sample sizes, or all possible samples of the same size? Okay, so that's what we mean by sampling distribution. So in other words, what is the distribution, the sampling distribution of x bar, given what I just said? Okay, so random variable x bar, right? Capital X with a bar. So that's our random variable x bar. Okay, so what is the sampling distribution of x bar? Well, we think that it's going to be approximately normal just from what I just said, right? So approximately normal would be great. Why would that be great? Because then we could use all the stuff that we learned in chapter 6 to calculate probabilities, right? So we would like x bar to be approximately normal. Okay? Well, that's where the central limit theorem comes in. The central limit theorem says that if our sample size is sufficiently large, then we can know with certainty that the distribution of x bar will be approximately normal with a mean and a standard deviation. Okay? And in fact, the central limit theorem works whether we know anything about the distribution of the population. So we don't need to know anything about the population as far as x. As long as our sample size is big enough, we can be assured that the sampling distribution of x bar will be approximately normal. Okay? Now, the question then becomes, well, what is large enough? Okay? Well, typically it's a sample size of 30 or more. Okay? So that's what we mean. That's the central limit theorem. So now what are the other things, well, that are consequence of that? Well, again, remember, we would assume that, it makes sense that the mean of the means, right, if we took the average of the means, the sample means, so if we took mu of x bar, right, we'll call it mu of x bar. So if we took the average of the sample means, this makes sense that that would be equal to mu, right? From what we just discussed, okay? Now, the other thing too that comes from the central limit theorem is that the standard deviation of x bar turns out to be sigma over the square root of n, okay? So the sampling, the standard deviation of the sampling statistic, the sample statistic, x bar, is less than the standard deviation of the population, okay? And that is also intuitive because, remember, from chapter 2, the variation from sample to sample for the mean, for the sample mean, is less than all the other statistics or all the other values for measurements of center, okay? And that was one of the things we talked about. So it makes sense that the standard deviation for the sample mean should be less than the standard deviation of the population, okay? Now, so what's the gist of this? So here's what it says, okay? Now, how big the sample needs to be depends on the population, okay? Now, if the population is normal, then we can have a normal distribution for even small sample sizes. Where the central limit theorem is really applicable is if we have skewed populations, okay? Or if we don't know anything about the population, okay? And in that case, that's where the condition of n has to be at least 30, okay? So let's look at let's keep going here, and I'll add on to this here. So here are the results of the central limit theorem. Okay? So the central limit theorem states this. Okay, let me get another marker. So here's what the central limit theorem states. Okay. Suppose that x is a random variable with a mean mu and a standard deviation of sigma. In other words, let's assume that x is a random variable that comes from a certain population, and we know the mean and the standard deviation of that population, okay? And that's all we know, okay? So if, given, let's say given. And this is shortened with CLT for short, okay? So given a population with a mean of mu and a standard deviation sigma. Okay, so that's what we have. Okay, so again, and x is the random variable, right? So given a population of x, right? So random variable x, what do I want to do here? So in other words, here we have x, right? So again, it could, the random variable x, it could be height, it could be anything, right? So whatever it is, the population is going to be a population of x values. So capital X for the random variable for the population values, okay? So given a population with a mean of mu and a standard deviation of sigma, it says that as the sample sizes increase, so as n increases, the distribution of x bar. So in other words, the sampling distribution, right, of x bar, the distribution of x bar, you know what, more accurately just to say the sampling distribution. So the sampling distribution of x bar becomes more and more normally distributed. More and more normal. Okay? With, now, again, with a mean of mu. So again, the mean of the means is mu. So again, mu of x bar is equal to mu, right? And a standard deviation of sigma of x bar, again, which is going to be equal to sigma divided by the square root of n. So again, here's the gist of it. So the central limit theorem says that, hey, if we are given a population with a certain mean and a certain standard deviation, then as our sample sizes increase, the distribution, the sampling distribution of x bar becomes more and more normal with a mean of mu and a standard deviation of sigma divided by the square root of n. Okay, that's it. That's what the central limit theorem tells us. Okay, and that's how it works. Okay, now, what is the size of n that helps us with normal? Well, the demarcation, or the cutoff is going to be 30. Okay, so if n, so in other words, if n is greater than or equal to 30, then x bar is going to be approximately normal with a mean of mu and a standard deviation of sigma with the square root of n. That's it. Okay? And this is what we're going to use to calculate probabilities based on now x bar, right? Up until this point, we've talked about probabilities of a random variable x, right? Probabilities of smiling times, probabilities of weights of newborn babies, probabilities of getting a particular score on an exam, so on and so forth, right? So those have been all x values. Now what we're going to do is we're going to use the central limit theorem to help us figure out probabilities of averages. Okay, what is the probability that the average weight of babies of a certain sample size is less than 5.5 pounds? What is the probability that the average score on an exam is less than this? What's the probability that the average bank account balance is going to be between two values? So now we're going to switch and we're going to answer questions about probabilities of averages, involving averages, where the central limit theorem is going to be the key to helping us figure out what those probabilities are. Because why? We'll be able to use the normal distribution and use all the tools from chapter 6 to help us do it. Okay? So now, let's continue. Okay, so let's say this. Okay, let's look at an example. Or actually, hold on a second. Yeah, no, that's it. Okay, so that's all I want to say. So let's use this as an example. So it says, an unknown distribution has a mean of 90 and a standard deviation of 15. Well, we don't know what it is, but what we do know is mu is 90 and sigma is 15. Okay. A sample size is 80. A sample size of 80 is drawn from the population randomly. So n is 80. A says, find the probability that the sum, oh, we don't want to do this one. Hold on a second. This is the one I don't want to do. We're not dealing with sums. We're not going to deal with sums. Hold on a second. Okay, by the way, you know what? I'm doing the wrong example. So one thing to note, just for vocabulary, because this is going to come up later, but what do we call this here? So if we have a population with a mean and standard deviation, and if x bar is normally distributed, then the mean is going to be mu, and sigma, the standard deviation, or the standard error of the mean, okay, so this is called x bar, right? So the mean of the means is going to be mu, and sigma of x bar, which is sigma over the square root of n, this is called the standard error of the means, okay? We don't call it the standard deviation of x bar, but it's the standard error of the mean, okay? That's typically that's what it's called. It's often called the standard error of the mean. Now, the thing is what makes this work, and we talked about this before, is the law of large numbers, right? So the law of large numbers, it says, hey, remember that as the law of large numbers stated, remember from probability, right? So the law of large numbers states, in chapter 3, we said that as the sample size gets bigger and bigger, that the sample mean gets closer and closer and closer to the population mean. Okay, that's the law of large numbers, and that holds for not only probability, but the sample mean, right? So in chapter 3, we talked about how the law of large numbers says that as the sample size gets bigger, the relative frequency, right, of an event gets closer and closer to the theoretical probability. So here, the law of large numbers helps us in that we know that the sample mean, as the sample gets bigger and bigger, it makes sense that the sample mean gets closer and closer to mu. Okay, so that's why we can get this. Okay, again, I've said that before, but just as a review. Okay, so here's what I want to do. Here's the z-score. So again, if this has a normal distribution, right? If n, right? So n is bigger than or equal to 30. We know this, right? So this is the central limit theorem. Gives us this. So what does this mean? If that's true, then we can use z-scores. We can calculate z-scores. Now the z-score formula changes a little bit. Okay, so the z-score formula is going to be, again, observed value minus the mean divided by the standard deviation. But in this case here, what's the observed value? The observed value is a sample mean. So it's going to be x bar minus the mean. Well, what's the mean? Mu, right? Doesn't change. What's the standard deviation? Well, it's the standard error of the mean, which is sigma divided by the square root of n. So now our z-score formula becomes this. Okay? So again, just remember the form. Observed value minus the mean divided by the standard deviation. All we're doing is now our observed value is x bar, a sample mean. Our mean doesn't change. It's still mu. So this is mu, right? So in other words, I could write it this way. X bar minus mu of x bar divided by sigma of x bar. Well, same form. Now we're just plugging in. It's x bar minus mu divided by the sigma divided by the square root of n. Okay? So now we know how to calculate a z-score for the average. So now we can use our norm CDF function. We could use a z-table. Again, everything from chapter 6 that we had in our toolbox comes back. Okay? So now let's do this. Okay. So now let's do the example that we were talking about before. So now here it says an unknown distribution has a mean of 90. So here we go. So mu is equal to 90, sigma is equal to 15, and now in this case, the sample size n is 36. And again, this is a random sample from the population. So now it says, find the probability that a randomly selected sample mean is between 85 and 92. So we want the probability that a randomly selected sample mean, x bar, is what? Is between 85 and 92. So that's what we want to find, right? So here's where we have to ask, we have to know what is the distribution of x bar, the sampling distribution. So what is the sampling distribution of x bar? Well, in this case here, it's going to be approximately normal. Why? Because n is greater than or equal to 30. So here, we don't know anything about the population. If we knew the population would be normal, then automatically we can assume that x bar is normal. Okay? Here's the thing. If the population is normal, we automatically know that the distribution of x bar is automatically normal. In fact, when the population is normal, it seems like everything turns out to be normal. Okay? But here we don't know that. We don't know anything about the population. So in this case, we have to use the central limit theorem. Here, n is bigger than or equal to 30, so the central limit theorem gives it to us. So we know that x bar is approximately normal with a mean of mu and a standard deviation of sigma divided by the square root of n. So in other words, what do we get? Well, mu is 90, so mu stays the same. Here, this becomes sigma, which is 15, divided by the square root of 36. So in other words, what does that become? Well, the square root of 36 is 6, and then we get 15 divided by 6. But again, you can just stick that in your calculator as we'll see. Okay? So now, how do I do this? Now that I know it's normal, this is what I'm going to use in my calculator, or I can use the table. So again, so let's do it both ways. If I use the table, right, I have to first transform it into a z-score. Well, I know mu and I know my standard deviation. So it's going to be x bar, right? And so I have to find both of these z-scores, right? And so once I find the z-scores, I have to use the table and subtract the areas, right? So if I want the z-score for this one, so let's call this x1, we'll call this x2. So z1 would be x bar 1 minus mu divided by sigma over the square root of n, right? So that's going to be 85 minus 90 divided by 15 over the square root of 36. And when I do that, I get what? I get, let's see. And so what do I get? I get -2. And z2 is going to be, oh, this is x bar, sorry. So this is going to be x bar 2 minus mu divided by sigma over the square root of n. And so we get 92 minus 90 over 15 divided by the square root of 36. And so if we do that one, we get what? We get 0.8. Okay, and so what we would have to do is we'd have to use the table, right, to get this probability, and this would give us area to the left, right? And then we would use the table for this one and find the area to the left of that one, right? Because that's what the table gives us. Remember, the table always gives us area to the left. And then what we would do is we would take this area, right? So we take the area to the left of this one and subtract off this area. And that would be the answer. But again, that's using the table. Let's use the calculator. A lot easier. Okay? So in this case here, we're going to use Normalcdf. So we're going to use Normalcdf. And so here we just put in the lower bound, the upper bound, the mean, and the standard deviation. So the thing is make sure you put in the correct numbers for the mean and standard deviation. Okay? So the lower bound here is 85. The upper bound is 92. And so what's the mean? Well, we're not going to use, well, the mean is actually going to be the same here, right? So 90. So it doesn't matter. So the mean is mu, which is 90. But the standard deviation, we don't want to use 15 because that's not the standard deviation of x bar. That's the standard deviation of x. What we want to use is this. So we want to use 15 divided by the square root of 30. And you can put it right in your calculator. So 15 divided by the square root of 36. And so if we put that in the calculator, we get 0.7654. 0.7654. And that's it. So I hope that makes sense to you. The biggest thing is we wouldn't have been able to do this unless we knew that this was normal. And how do we get that this is approximately normally distributed? The central limit theorem. N is bigger than or equal to 30. That's it. And then, so this is the biggest key. This is what makes the whole thing work, the central limit theorem. Okay? So now, B says find the value that is 2 standard deviations above the expected value of the sample means. So in other words, find the value that is 2 standard deviations above the mean. What mean? The mean of x bar. Okay? So in other words, we want to know what's the probability that x bar, or excuse me, it says find the value. Okay, so find the value. So here it is. So we want here. So here's the distribution, right? So here's the mean, right? And we want this x value. That's 2 standard deviations. So this is, okay. So we want the x value that is 2 standard deviations above the mean. That's what they want. Okay. So how can we do this? Well, we can use the standard deviation of x bar. We have the distribution. We know it's centered at mu. Well, what's 2 standard deviations above this? Well, the mean is what? 90. Well, the standard deviation is what? 15 divided by square root is 36, which is 15 divided by 6. And so that's going to be 2.5, right? So 2.5 is the standard deviation for x bar. So if we go 2 standard deviations above 90, well, what is that? That's plus 2.5. That'll take us here. Plus another 2.5 will take us right there. So it's 90 plus 5. So this is 95. So that's the x value. That's it. Okay? So all we did was added 2 standard deviations to 90, and that's the answer. So the answer is 95. Okay? Now, we could have also used inverse norm, but this was the easy one. So inverse norm, what do we have to do? We have to put in the area to the left. Well, we have to use the empirical rule. We could use the empirical rule here, right? So what's the area to the left if we go with 2 standard deviations? Well, within 2 standard deviations is 95%, which means that there's 5% left over. So that means 2.5 is in the lower tail. So what do we have to put in? It's going to be 0.975. And then what do we need to put in? Well, the mean and the standard deviation. So the mean here is 90, and the standard deviation is 2.5. And we'll get the same answer. Okay? So again, we could use inverse norm, or we could do, this one's the easier route because since we have the mean and standard deviation, it's easy just to add 2 standard deviations and get our answer. So the answer is 95. Okay? So that's where I'll stop. So we're going to continue on with chapter 7, and we'll start part 2, and we'll start as far as using it to apply to other types of problems. But this is pretty much what we're going to continue to use. Okay? Thank you, and I'll see you next time.